Let us now turn our attention to another problem, and that is, how does one apply Newton's second law to an arbitrary system? What do I mean by an arbitrary system? Well, we know how to apply Newton's second law to a system which can be made of one object only, made of more than one object, or made of only a part of the same object. But there is something that must be the same for everything within that system, and that is they must have the same acceleration. Every part of the system must have the same acceleration, because if it's not the case, when I say F equals ma, what A is it? Is the A of this guy or A of that guy? You know, if these two guys, if I want to apply Newton's second law to them as the same system, then what we have learned so far is that these two objects must have the same acceleration. So for example, I can use a string to link them. Okay, if I use a string to link them, and then I pull on this mass with a certain force F, both of them will move with the same acceleration. That is why I can put them in the same system, and of course the force, the tension in that string becomes the internal force, which I don't have to consider when I try to find the acceleration. But I can of course separate them into separate systems, object 1 and 2, but whatever you do, make sure you know that every part of the system has the same acceleration. In this case, we have a rope. We don't consider the entire rope necessarily, all at once. We consider a segment of the rope, and let's say, all right, we got forces exerted on this rope. We got a force this way, we got a force that way, and we can find the net force exerted on this segment. We can figure out how this segment moves, that sort of thing. So you can have one object, more than one object, or only part of the object, but everything within the system that we choose must have the same acceleration. That's the bottom line. But when we say apply Newton's second law to an arbitrary system, then we are looking for something beyond that restriction. And that is, now we can remove the condition that everything within the same system must have the same acceleration. I can consider just a random collection of particles, say a piece of cloud, okay, and everything within our system may or may not have the same acceleration. Just put everything together like this. This guy accelerates this way, that guy accelerates that way. They can have totally different acceleration. Is it possible to include all these particles with different acceleration into the same system? That is what I mean by an arbitrary system. Of course, if we can do that, we have certainly extended the applicability of Newton's second law beyond what we have learned yet. And that calls for the concept of the so-called center of mass. Here is our system. It's made of a whole collection of particles, each with a totally different acceleration in principle. Our job is to write down some sort of F equals ma for this system. Okay, now, of course, every object, every particle within the system is subject to two kinds of forces. One is a force from the outside, okay, from a source outside the system, and the other is a force from another part of the system to it. For example, the force between the red particle and the black particle. The red particle can give a force to the black particle, but that force is internal, right? Because it's from one part of the system to another. So those forces will not survive when I consider the entire system all at once, because the action cancels reaction. I only have to consider the external forces. So you can imagine if I wrote F equals ma for this entire system, F would be the sum of all the forces acting on every object within the system, and the internal forces, such as the force between the black and the red one, will eventually cancel out because of action and reaction, but the external forces will survive. Okay, so this is what I imagine the force would be, the sum of all the external forces acting on every one of them. We want to be equal to mass times the acceleration. Okay, of course, I'm considering right now the case when the mass does not change. If the mass changes, it's another matter we'll discuss later. So let's say F equals ma. What do you think that mass should be? Well, common sense. It should be the sum of all the masses, right? Because this is our system. The entire mass is m. So it's easy to figure out what the force should be, what F should be, what m should be. But what about acceleration? You know, the sticky point here is that acceleration of every object is now different. I cannot pick up this red particle and say, let me choose this acceleration, because the others may not have the same acceleration. So here's the thing. Which point is it, when I say F equals ma, a is the acceleration of something, right? Of some point, right? Which point is it? Well, you know, that got to be a special point. It's got to be a special point. What point is that? Well, as you probably have guessed, that point is called the center of mass. Where is the center of mass? Well, let's see. You know, I don't know yet how to write down Newton's second law for this entire system in one gulp. Okay, all I know is how to write down Newton's second law for each individual particle, because every particle has the same acceleration within itself. So why don't I do this? Why don't I start with something I know? That is, let me label the particles 1, 2, 3, 4, 5, 6, whatever. Let's say here is the ith particle. Okay, here's the ith particle. Let me write down Newton's second law for the ith particle. I can be 1, 2, 3, 4 all the way to n if there are n particles within a system. Okay, how do I write down the Newton's second law for the ith particle? Well, it says F equals ma, and let me apply it to this particle, and that's relatively simple. Let me draw another diagram here. Here is the ith particle right here. Okay, the ith particle, and I must first of all identify its location using a displacement vector r sub I, starting from the origin of the coordinate system. Okay, here's a fixed origin of the coordinate system. Here's the ith particle, and this guy can have a certain acceleration a sub I. So let me write down Newton's second law applied for this guy only, and I have F sub I, the forces exerted on the ith particle, including those from the outside and those from other parts, from other particles within the same system. And all the forces, okay? It's mass of the ith particle times the acceleration of the ith particle, right? That was F equals ma. Now, look at what I want to do next. I want the left-hand side of the final equation to consist of all the forces, the net force on all the particles. This is only the force on the ith particle, right? So what do? Well, imagine I wrote this formula. I wrote Newton's second law for the first one, second one, third one, fourth and fifth one until the nth one, right? So I have n equations, right? So I, on this left-hand side, I have F1, F2, F3, F4, and so on. But here, in the eventual single equation for the entire system, on the left-hand side, I want the sum of all the forces. That's the net force, right? So how do I get the sum of all forces from F1, F2, F3, and so on? Yeah, let me just add every equation up, right? So on the left-hand side, I would have the sum of all forces, right? So let's do that. Let's sum over all the equations, okay? I goes from 1 to n if there are n particles. And that should be equal to the sum of the right-hand side, right? 1 through n, m sub I, a sub I. Here we go. Okay, now when you add all these forces up, again, only the external forces survive. The internal forces, such as the force between these two particles, will just cancel out because of their action and reaction. Okay, so the left-hand side is simple. The left-hand side is exactly what we're looking for, sum of all the external forces, okay? External forces. Let's look at the right-hand side. The right-hand side, we have to clean up a little bit, because the way it is now, it's m1a1 plus m2a2 plus m3n3 and so on. What I want is I want to single out the total mass. There is no explicit total mass here, because you don't have m1 plus m2 plus m3 so on. Rather, you just have m1a1 plus m2a2. M and a are mixed up here. So what I'm going to do is I'm going to force it, okay? Let me force an m out. That's the total mass. Of course, when you force the total mass out, you're going to have to divide this by m. Okay, you're going to divide this because you multiply by m, you have to divide it by m. So there we go. Let me see what's left. M sub I, a sub I, divided by m, right? M and m cancel, so these two, of course, the same. Let us take a closer look at what I have here. This looks like a mess, but if you take a closer look, you find, first of all, the dimension of this whole thing, this quantity, is that of the acceleration. After all, the mass, these two dimensions cancel. You have this basically a whole bunch of accelerations. You add them up, you still get acceleration. So this is some sort of acceleration. Okay, It's some sort of acceleration, but is what acceleration is it? Well, regardless of what it is, we do realize that if we call this A, whatever acceleration that is, then I have successfully written down a single equation. Net force on the entire system equal to the total mass times that particular acceleration. I have succeeded in getting what I wanted, except that this acceleration is not the acceleration of any point necessarily. It's not the acceleration of object 1, 2, 3, 4 necessarily. Rather, it is some sort of combination. Okay? In order to find the acceleration here, you must do some sort of summation over all the particles within the system, and you find this particular acceleration. This is the acceleration of a special point within the system, and that special point is called the center of mass. Where is the center of mass? Well, you see here, we assumed that the particles, the masses do not change. M1, M2, they're all constant. So A equals this guy. Okay, so I'm going to write ACM now because I identify this point to be the center of mass, because after all, it's a special point, right? It's as if, you know, all the forces, all the external forces are exerted on this single point, which has all the mass m concentrated on it. So it must be a special point equal to the center of mass. So what is ACM equal to then? Well, take a look. ACM equals to this. ACM equals this. MI, AI, capital M. It is the second derivative of a displacement vector with respect to time. You know, acceleration is always the second derivative of displacement vector, right? That displacement vector would start from origin and will point at a special point called the center of mass. It's not just any other point, but a special, one and only special point, center of mass. This would be so-called RCM. Okay, the position vector from the origin to the center of mass, which is right here. We call it RCM. Where is RCM? How do you figure out RCM? Well, simple. The mass is a constant. Okay, so if I integrate A over time, what do I get? I get V, right? I get VCM and V sub I. Integrate another time over time, then I go from V to what? To R, right? So indeed, the center of mass position, RCM. This tells you how to locate the center of mass. Okay, it is just equal to the sum MI R sub I over capital M, the total mass. This is the expression for the position of this unique point called the center of mass. So it's M1 R1 plus M2 R2 plus divided by M. Okay, it takes into consideration all the particles within the system, but it's just a single location, a single point. And here is our system. If I go back to the original, here's our system, and you label it 1, 2, 3, 4, 5, whatever, and you, for each of them I have a position vector, and I sum these position vectors over according to this formula, and then I locate the center of mass. I end up at, say, this point. Okay, the center of mass, I end up at this point. And then if I draw a position vector from the origin of the coordinate system to that particular point, I get RCM. What is so special about RCM? It is not just any point. The thing about RCM is that when you apply Newton's second law, okay, when you apply Newton's second law, you can pretend that the entire system is concentrated at this one spot called the center of mass. It has all the mass of the entire system, and it has an acceleration A cm, which is determined by the net force exerted on that system, F external, for the entire system. F equals m times ACM. Okay, so you look at how this particle, the center of mass moves from a reference point O. You trace the center of mass movement. You find that as far as the center of mass movement is concerned, you don't really have to worry about where every particle is. You just focus on attention on one point, which is center of mass. It's got all the masses of the entire system, and it's subject to all the net forces exerted on the entire system, and it moves accordingly. F external equals total mass times ACM. As if it was just a single point mass influenced by the net force. Okay, so basically the idea was we use this special point called the center of mass to reduce this multi-particle system into a single particle system. That single particle is located at a special point called the center of mass of the system, and the motion of that single point is not influenced by any internal force between, say, the second particle and third particle within the system. It is only influenced by the external force. Okay, and how does one locate the center of mass? Well, we had a formula written down here. That's the formula, that's the vector formula. And this RCM has three components, x, y, and z. Okay, so for x component, this is x sub xcm, so that's the x component of the position vector of the center of mass, and that r sub I is replaced by x sub I. For ycm, the y coordinate of the center of mass, I replace it with y sub I, and so on. So I end up with these three component formulas. Okay, xcm equals this, 1 over total mass times x sub I m sub I. When we take a closer look, you find what we're doing here is we're just taking some sort of average over all the x coordinates. Okay, but the average is not totally a straight average. It is not equal to x1 plus x2 plus x3, so on, so on, so on, and divided by the total number of particles. No, that would be a straight average without any weight. This is what's called a weighed average. Okay, not every particle in a system is created equal. Some particles are more important than others. Why are they more important? Because they have more mass. Okay, so basically you take the mass of this particle multiplied by its coordinate. So if this guy is more massive than others, then it has more say in determining what the center of mass is. Okay, so if the system is made of two halves. Okay, there's a heavier half, there's a lighter half. Then of course the center of mass will be tilted towards the heavier half. That is due to the nature of the center of mass. You consider it as the weighed average of the position of the system, of all the particles in the system. What's the weight that you use? It's the mass that you use. Yeah, if a particle has twice the mass, it has twice the importance in determining the center of mass position. Okay. Also, this is when I consider a discrete set of particles. I can have actually point masses 1, 2, 3, 4. I can count. What if the mass is uniformly or continuously distributed? Say a rod. Okay, a rod with uniform mass distribution. What do? Well, then I have to sum over infinitesimally small pieces, right? And the summation becomes a summation over infinitesimally small segments, and that naturally becomes an integral. I don't use the subscript I to do it anymore. I just cut it into small pieces, infinitesimally small pieces, dm. That x, what's x? X is the coordinate of that mass dm, of this little segment dm. Okay, so I have to perform an integral. We'll see examples of how that works. If you know xcm, you also know y and zcm, so on. Again, why is the center of mass so important? Because the center of mass is the one and only unique point such that its motion has nothing to do with internal forces. Its motion is determined only by the net external force on the system. For example, I have this wrench here, okay? And if I perform this calculation and find the center of mass is right here, that's the position of the center of mass. I mean, it makes sense. You quantitatively see the head has more mass than than this part of the tail, right? So the head is heavier than this part of the tail. That's why the center of mass is a little bit over there towards the heavier part. So somewhere here. Okay. Now, if I throw this wrench into the air, all right, if I throw this wrench into the air, the motion of the wrench can be, in principle, complicated because not only does it sail through the air, but also can flip and flop, can do all kinds of weird things. In fact, here is the position of the wrench at one point. At the next moment, the wrench may look like this. And the next moment, it may look like this. And the next moment, it may look like this. You know, it is flipping and flopping. Okay? It is flipping and flopping. And if you look at, say, this point, the tail of the wrench, it does a complicated motion, okay? Can be wavering all over the place. The reason why the motion can be so complicated is because if you look at the tail section, the motion of this tail section is not only influenced by the weight of itself, but also it's influenced by another part, by the other part of the wrench. But of course, that's only internal force. Internal forces can influence motion of other points, but it cannot influence the motion of a special, unique point, and that is the center of mass. The center of mass only cares about external force. It only responds to external force. As a matter of fact, if I connect these red dots at various time, okay, this is like a multiple exposure at different times, and if I trace this red dot at every point, I find that unlike any other point, this red dot, the motion is extremely simple. What is it? It's a parabola. Okay, you throw into the air. Why the parabola? Because this red dot cares only about the external force, which is gravity. Under the influence of gravity, how does a point particle move? Projectile motion, of course. The curve is that of a parabola. So the head and tail or any other point may be executing a complicated motion, can be dancing around all over the place, but the center of mass does map out only a beautiful parabola because it can only respond to one force, mg, m being the total mass of the system. So the center of mass truly is a unique point.